Hello everyone, welcome to the 25th lecture of the course Discrete-time Markov chains and Poisson processes. So, in the last lecture we finished the discrete-time Markov chains part of the course. So, today we will move on to the Poisson processes part, but actually we will not start with Poisson processes today. Before starting Poisson processes, we need to learn something more about exponential distributions. That is what we will be looking at in today's lecture. So, you already know what is an exponential random variable. So, we will just recall that. So, a random variable x is said to have exponential distribution with parameter lambda greater than 0 if the probability density function of x is given by this quantity. So, it is lambda times e to the power minus lambda x if x is greater than 0 and it is 0 if x is less than or equal to 0, fine. So, random variable x is said to have exponential distribution with parameter lambda greater than 0 if it is a continuous random variable with probability distribution defined in this way. So, again this kind of things, so you already know what is an exponential distribution from your basic knowledge of probability. So, it is just a recall. And what is the cumulative distribution function of x? So, it is given by this. So, you know that if it is a continuous random variable, then its distribution function is given by integration minus infinity to x fxx dx. So, you know fxx is this. So, if you just do the integration, you can easily check that the cumulative distribution function of an exponential random variable is given by this. So, it is 1 minus e to the power minus lambda x if x is strictly greater than 0 and 0 otherwise. So, this is a random variable which takes only positive real values. So, it does not take non-negative real or non-positive real values. So, that is an exponential distribution or a random variable having exponential distribution, and we will use this notation. So, x tilde exp lambda. So, we will use this notation to mean that x is a random variable with exponential distribution having parameter lambda greater than 0, fine. So, that is exponential distribution. Like you also know many properties of exponential random variable, like for example, if you calculate, you can easily check that what is expectation of x. So, first of all, expectation exists and it is equal to 1 over lambda. Similarly, you can calculate what is variance of x and so on, fine. Okay. So, that is exponential distribution or exponential random variable. Now, these are some plots of PDFs and Cdfs of exp lambda for several values of lambda. So, you see we have plotted here for 3 different values of lambda, lambda equal to 2, lambda equal to 1 and lambda equal to 0.5. So, you see the smaller the lambda for PDF, it decays much slower, or the higher the lambda, the decay is much faster. And similarly, if you look at the cumulative distribution function, the bigger the lambda, the higher it goes towards 1, right. So, you see the blue curve goes towards 1 in a at a much faster rate, or it goes much quicker to 1 as compared to the green or red curve, and similarly here you see the blue curve decays much faster as compared to the green or red curve. So, again, so these are just some observations from the PDFs and CDFs of exp lambda for several values of lambda. Again, you must have seen all these things in your basic course on probability, right. So, again, as I said, like this part is just simply recall, fine. Okay. Now, we will start with some properties of exponential distribution which we will be needing for Poisson processes. So, the first property is what is called the memoryless property. So, that we state as a theorem. So, what is the theorem? Suppose x has exponential distribution with parameter lambda, and so everywhere we will not say lambda greater than 0, but whenever we say that x has exponential distribution with parameter lambda, we mean that lambda is strictly greater than 0. Then for any Ts greater than or equal to 0, if you look at this quantity, that probability x is greater than t plus s given that x is greater than t. That means what is this quantity? So, you are told that x is greater than t and you are being asked what is the probability that x will be greater than t plus s, right. So, you have been given, so it is a conditional probability, you are given the information that the value of x is greater than t and you are being asked that okay, what is the chance or what is the conditional probability given this information that the x will take value greater than t plus s. Now, what this property is telling you or what this theorem is telling you that is just simply probability x greater than s. Now, this is what is called the memoryless property. Why? Now, what is this saying? It is saying that this information that x is greater than t. So, you know that okay, x is greater than t and you are asking what is the probability it will be greater than t plus s. Fine. What this is saying is that this information that it is greater than t is actually not like is being used in the sense that this is same as just probability x greater than s. Now, why am I calling this as memoryless property? Now, let me explain it in giving an example. Now, think of suppose lifetime of of some electronic gadget, say lifetime of a bulb. Suppose it follows exponential distribution. Fine. Suppose the lifetime of an electric bulb follows exponential distribution with parameter lambda. Then what this probability x greater than t plus s given x greater than t means? That means you are told that the bulb has already lasted or has already survived for t units of time. And what is the chance that it will survive an s additional units of time. So, you are told that okay, it has already survived for t units of time and you are asking what is the probability that it will survive for t plus s units of time, or in other words you are asking what is the probability that it will survive for additional s units of time. Now, what this theorem is telling you that is same as the probability that the bulb will just survive s units of time. So, this information that it has already survived for t units of time is not being used or is not useful. So, when you are looking at a bulb, so you don't, if you know that the bulb has the lifetime of the bulb follows an exponential distribution, then suppose you just come to inspect a bulb, you don't need to know how long it has been working in order to answer the question that how much further it will work. So, that is what this property is saying. That is why it is called memoryless, because it does not have any memory. It does not keep in memory that it has already survived for t units of time. So, when you are asking okay, what is the probability that it will survive for s additional units of time, it is as if it is assuming that the bulb, so it's new bulb, it is forgetting that okay, it has worked for t units of time, right. That is why it is called memoryless property. So, that is what this probability x greater than t plus s given x greater than t equal to probability x plus s. If you have to think of it in a real life situation, this is what it is saying. Fine. Further, exponential distribution is the only continuous distribution, or it is the only continuous random variable with this property. So, it is kind of an again if and only if statement. So, if x is an exponential random variable with parameter lambda, then it satisfies this property, and if you are, or it is what is called this memoryless property. Similarly, if you are told that okay, x is a continuous random variable having this property, then straight away you can say it is an exponential random variable with some parameter lambda greater than 0. So, if it is an exponential random variable, then it has the memoryless property. Similarly, if you are told that okay, it is a random variable which has the memoryless property, then it is for sure the exponential random variable. That is what is that. So, this is what is an if and only if statement. So, it is memoryless if and only if it is an exponential random variable. Fine. Okay, now you will see proof, but again we will just prove the first part, that if it is exponential then it has this memoryless property. We will not prove this other part, that if it is a continuous random variable with the memoryless property then it is exponential distribution. That proof is slightly complicated, we will not prove it in this course, but we will see one side of the proof, that if it is an exponential distribution with some parameter lambda greater than 0, then it satisfies this memoryless property, or it has the memoryless property. So, we will look at this probability x greater than t plus s given x greater than t. So, we are using the formula for conditional probability. We know that probability A given B is probability A intersection B divided by probability of B. So, this is nothing but probability x greater than t plus s intersection x greater than t divided by probability x greater than t. Now, probability x greater than t plus s intersection probability x greater than t is just simply this. Why? Because if x is greater than t plus s, then for sure it is greater than t. So, this set where x is greater than t plus s, it is a smaller set, because if x is greater than t plus s, then for sure it is greater than t, but not other way. If it is greater than t, you cannot just say it is greater than t plus s. So, this set of all omega for which, so if you look at this set of all omega for which x of omega is greater than t plus s, that is a subset of all omega such that x of omega is greater than t. So, this intersection this is this. So, if you have a smaller set and a bigger set, so if A is a subset of B, then A intersection B is A. So, that is why we get that this is basically, so probability x greater than t plus s intersection x greater than t is just simply probability x greater than t plus s divided by probability x greater than t. Now, you know it is an exponential random variable, so you know what its CDF is. So, now so this probability x greater than t plus s will be just 1 minus f of t plus s. So, that you get as e to the power minus lambda times t plus s, and the denominator is probability x greater than t. So, it is e to the power minus lambda times t. Now, if you just do the cancellation, you get e to the power minus lambda s, which is simply probability x greater than s. Fine. So, we have proved that if x is an exponential distribution with parameter lambda, then it has the memoryless property, which is that probability x greater than t plus s given x greater than t is just simply probability x greater than s. So, this distribution does not have memory. So, if given that an electric bulb has survived for t units of time, and if you are been asked that what is the probability that it will serve for s additional units of time, that is same as asking what is the probability that a new bulb will survive s units of time, right. That is the memoryless property in real life situation, provided you are told that the lifetime of the electric bulb follows exponential distribution with some parameter lambda strictly greater than 0. Fine. Okay, so that was the first property. Now, second important property. If x1, x2, xn are IID, that means independent and identically distributed random variables with having distribution exponential lambda. So, each xi is exp lambda and xi's are independent of one another. Fine. So, that is the meaning of x1, x2, xn are IID exp lambda. Then if I look at this sum random variable, so Sn I running from 1 to n xi, now what this theorem is telling, that then the sum is again a continuous random variable having this probability density function. Now, if you have seen this density before, then you should know that this is the density of a gamma n lambda distribution. Fine. So, this is the density of a random variable which has gamma n lambda distribution. Fine. So, what this theorem is telling you is that if x1, x2, xn are IID exponential lambda, then if you look at the sum x1 plus x2 plus so on up to xn, then that has gamma n lambda distribution. What is gamma n lambda distribution? It is a continuous random variable having probability density function equal to this. Again, you must have seen gamma distribution or gamma distributed random variable in your basic course in probability. So, if then this density should be familiar to you, but anyway, if you have not seen this before, then if x1, x2, xn are independent and identically distributed exponential lambda random variables, then if you look at the sum, then it has gamma n lambda distribution, which is that it is a continuous random variable having this probability density function, right. Now this is true for any n, so we will prove it by mathematical induction. Now, it is easy to see that this is true for n equal to 1. N equal to 1 means you are just looking at x1, but what is x1? x1 has exponential distribution, and what is the density? The density is lambda e to the power minus lambda s for s greater than 0, 0 otherwise. So, now if you compare this and this, now remember what is gamma n? Gamma n is n minus 1 factorial. So, that is the formula. So, if n is for, then this is true for any n greater than or equal to 1. So, and also 0 factorial is equal to 1. So, if you plug in n equal to 1 here, so you get lambda divided by gamma 1, which is 0 factorial, which is 1. Now, s to the power 1 minus 1, so s to the power 0, that is 1, e to the power minus lambda s. So, you get precisely this thing, that the density is lambda times e to the power minus lambda s for s greater than 0. So, if I just look at for n equal to 1, that means I am just looking at a single random variable. Since this is exponential, since this has exponential lambda distribution, so its PDF is given by this, and if you plug in n equal to 1 in this formula, then you just get this using the facts that gamma n is n minus 1 factorial and 0 factorial is equal to 1. Fine. So, how does mathematical induction work? You first prove it for n equal to 1 or n equal to 0 depending on the situation. So, here we prove it for n equal to 1. Now, we assume it for some k minus 1 and then you prove it for k, that this assumption that it is true for k minus 1, that is what is called the induction hypothesis. So, we assume that it is true for n equal to k minus 1. So, this is what is called induction hypothesis. So, we assume that it is true for n equal to k minus 1. Fine. Now, we will show that this is true for n equal to k. That is how, that is the process or method of mathematical induction. Now, if x and y are two independent continuous random variables. So, okay, before going to the final step, which is the inductive step, we need one more fact. So, the fact is, if x and y are two independent continuous random variables with probability density functions f and g respectively, remember independent is important. So, if it is important that x and y are independent. So, if they are two independent continuous random variables having probability density functions f and g respectively, then if you look at x plus y, the sum, that is again a continuous random variable with probability density function given by this formula. This is what is called the convolution formula. Again, the name does not matter, but this is the formula. So, if x and y are two independent continuous random variables, independent is very, very important. If x and y have some dependency, then this formula is not true. So, if x and y are two independent continuous random variables having probability density function f and g respectively, then if you look at the random variable x plus y, that is again a continuous random variable having probability density function given by this formula minus infinity to infinity f of s minus t gt dt. So, this formula is what is called the convolution formula, but anyway the terminology does not matter. Now, we will use this fact and the induction hypothesis. Induction hypothesis is we have assumed that, so we have assumed that this thing is true for n equal to k, that if I look at I running from 1 to k xi, that is a continuous random variable having this PDF for n equal to k, fine. So, now we want to prove it for k n equal, so we have assumed it for n equal to k minus 1. So we have assumed this for n equal to k minus 1. So, I equal to 1 to k minus 1 xi has this density with n equal to k minus 1. Now, we will prove it for n equal to k. So, we want to find the density of sk, which is k running sum over I running from 1 to k xi. So, again, so now remember, since this each xi's are independent, now if I look at sk minus 1, remember what is sk minus 1, that is I equals 1 to k minus 1 xi, and you have xk. Now, since xi's are IID, sk minus 1 and xk are independent. So, these two are independent, sk minus 1 and xk are independent. Again, both these are continuous random variables having some probability density function. So, using this fact, the density function of f sk, so which is sk minus 1 plus xk, by using this fact we get should be equal to this. But now, see, first of all, fxk, remember this is an exponential random variable. So, this is only positive for when t is so this should not be t. So, this should be s, this is s, this is s, fine. So, fxkt, remember xk is exponential. So, exponential random variable, its density is positive only for t greater than 0. So, the part minus infinity to 0 vanishes. Again, if you look at this part, remember this density is positive only when this argument is positive. So, this thing is positive only when t is less than s. So, finally, this integral limit becomes 0 to s, because outside that either this is equal to 0 or this is equal to 0. So, this first part is equal to 0 for t less than 0, and this second part is equal to 0 for t greater than s. So, finally, you get this integral from 0 to s, remember. So, this is a typo, it should not be t, it should be s, fine. So, integration 0 to s, this thing. Now, if you just do the cancellation, so here this is 1 e to the power lambda t, this e to the power minus lambda t, all those things will get cancelled. The integrating variable is t, so e to the power minus lambda s will come out. This, there is one lambda to the k minus 1, here there is a lambda, so you get lambda to the power k, and again this gamma k minus 1, fine, e to the power minus lambda s. Now, if you do this integration, you will see you will just get this is equal to, so just this integration is equal to sk minus 1 divided by k minus 1. Now, remember what is gamma k minus 1? Gamma k minus 1 is k minus 2 factorial. Now, with k minus 2 factorial, if you multiply k minus 1, then you end up with, so if you multiply k minus 1 times k minus 2 factorial, you get k minus 1 factorial, which is nothing but gamma k. So, doing all this, you finally end up with this. So, you have shown that this, that sk has precisely this density. So, it has this density for n equal to k. So, by mathematical induction, we have proved the result for all n. So, if x1, x2, xn are independent and identically distributed exponential lambda random variables, then if you look at the sum, which is x1 plus x2 plus so on up to xn, then it has what is called gamma distribution, and the meaning gamma n lambda distribution, and the meaning of that is it is a continuous random variable having this particular density. So, again this is 0 for s less than or equal to 0, and it is equal to this for s strictly greater than 0, and we have proved it by mathematical induction. So, we have shown first that it is true for n equal to 1, because when it is n equal to 1, it is just x1 and it has exponential distribution. Then we assume it for n equal to k minus 1, and then we prove it for n equal to k. But in order to prove it for n equal to k, we need this important fact that if x and y are two independent continuous random variables having probability density functions f and g respectively, then if you look at the sum x plus y, that is again a continuous random variable and which has density given by this formula. So, remember, it is very, very important that you have independence of x and y. This, if x and y has some dependent structure, then this formula is not true. Now, using that fact and induction hypothesis, we show that sk also has the correct density, right. So, the fact we using the fact we get this first formula, and then we just write down the densities, do the integration, and finally we end up with the correct result. So, by process of or by method of mathematical induction, we have proved our result. Fine, okay. Now, moving on to the last property that we will be seeing in today's lecture. So, again we have a theorem. If x1, x2 so on up to xn are independent exponential lambda I, now we are each xi's are independent, but they are not identically distributed. Each xi has exponential lambda I distribution. So, the parameter, so each of them is exponential, but the parameter can be different for different random variables, but independence is required. So, if x1, x2 so on up to xn are independent exponential lambda I, then if you look at this random variable which is minimum over I xi, then that again has an exponential distribution where the parameter is sum of all these parameters. Fine. So, for example, if I just look at two things, say x1 and x2, fine. Then, and suppose this has parameter lambda 1 and this is parameter lambda 2, then if I look at minimum of x1 and x2, that will have exponential lambda 1 plus lambda 2 distribution. Fine. So, if you look at independent exponential random variables, minimum of that, then that is again an exponential random variable where the parameter is sum of the parameters of the random variables whose minimum you are taking. Remember, again, independent is crucial. You do not have this if there is some dependence structure. Even if the marginal distributions are exponential, but if there is some dependent structure, this is not true. Independence is very, very crucial. Now, the proof is very simple. So, for t greater than 0, again, so if since each xi takes values only greater than 0, because each of them are exponential, so the minimum will also take value greater than 0. So, we only need to check for t greater than 0, because the probability that minimum will be less than or equal to 0 is 0. So, probability minimum over I xi greater than t, that means, so if minimum is strictly greater than t, that means each of the random variables is strictly greater than t. So, you get x1 greater than t, x2 greater than t and so on, xn greater than t. But now remembers xi's are independent, and so if you have independent, then probability of intersection is product of the probabilities. So, you get probability of this probability is basically product of this xi greater than t, I running from 1 to n. So, this follows from independence. Fine. Now, since each xi is exponential random variable, we know what probability xi greater than t is, that is just e to the power minus lambda I t, product I running from 1 to n. but if you do product of exponentials, the exponential just gets added, the thing in the exponent just gets added. So, this product is equal to this, but this is precisely nothing but the, so this is equal to 1 minus f(x) of t, where f(x) of t is 1 minus e to the power minus this sum over I lambda I t, fine, and this you know is precisely the CDF of exponential lambda. So, we get that since like there is this one-to-one, so you can identify a random variable from its distribution function. So, as soon as we know that, so here we are not exactly looking at the distribution function, but 1 minus the CDF, but if you have 1 minus CDF from there, you can easily find the CDF. So, we have seen that the CDF of this minimum random variable is equal to 1 minus e to the power minus summation over I lambda I times t. So, which is precisely the CDF of exponential random variable with parameter I running from 1 to n lambda I, hence we have shown the result. So, again you see we have crucially used independence in our proof. So, actually there is one more theorem that we are going to see in today's lecture. So, that the previous one was not the last. So, but this is going to be the last property that we are going to see in today's class. So, again we have another theorem which says that again if x1, x2 and up to xn are independent exponential lambda I. So, again independence is required, but we are allowing that each xi can have its own parameter lambda I. Then the probability that xi equal to minimum over j xj is equal to this. That means what is the probability that, so in the previous theorem was how is the minimum, what is the distribution of the minimum if xi's are independent exponentials. Now, this property says like what is the probability. So, suppose you are given n independent exponential random variables, what is the probability that say x1 will be minimum of x1, x2 up to xn? What is that probability? Or what is the probability that the ith random variable will be the minimum of this n among this n random variables, right? So, what this theorem is telling, that probability is equal to lambda I divided by sum over j lambda j. So, this lambda I corresponds to this I. So, the probability that xi will be the minimum is given by the parameter of xi divided by the sum of the parameters. So, it is kind of an intuitive result, right. So, the probability that the ith random variable will be the minimum among the n random variables is equal to the parameter of I divided by the sum of the parameters. Now, the proof, so it says for any n, so we will just prove it for n equal to 2. So, using this idea you can prove it for any n. So, but we will see it just for n equal to 2, but this the idea should be clear from this proof. So, we are interested in what is the probability that x1 is equal to minimum of x1 and x2, right. But that is same as probability that x1 is less than x2. In that case only x1 will be minimum of x1 and x2, fine. But what is probability of x1 less than x2? So, here we are using this conditional formula which you have seen in the preliminary. So, probability x1 less than x2 is integration 0 to infinity probability x1 less than x2 given x1 is equal to x multiplied by the density, fine. So, you have seen this formula in the just the first few lectures that you saw, which was the preliminaries. So, probability x1 less than x2 is integration 0 to infinity probability x1 less than x2 given x1 is equal to x times the density dx, fine. So, you have seen this formula, but now you know that x1 and x2 are independent, fine. So, now if you are told that x1 is equal to x, so you are told that x1 equal to x, but then this just becomes probability that x2 is greater than x given that x1 equal to x, but now x1 and x2 are independent. So, that conditional, so the unconditional probability will be same as unconditional probability. So, this is basically now becoming probability that x is less than x2 given x1 is equal to x. But now if you look at this, since x2 and x1 are independent, now this conditional probability will be just equal to the unconditional probability. That is because x1 and x2 are independent. Fine. So, that is where we are using independence. Fine. So, this is where we are using independence. Fine. So, this becomes equal to this. But now again you know x2 is exponential with parameter lambda 2. So, probability x2 greater than x is just simply e to the power minus lambda 2x times this density. But now, so this lambda 1 will just come out. So, this will inside integration it will be just minus lambda 1 plus lambda 2 x. Now, the integration of that, and then if you plug in the limits you will just get lambda 1 over lambda 1 plus lambda 2. So, this integration you can easily do. So, we have got that probability that x1 will be minimum among x1 and x2 is given by lambda 1 over lambda 1 plus lambda 2. Similarly, if you would have tried to check that what is the probability that x2 is equal to minimum of x1 x2, then you would have got the answer as lambda 2 over lambda 1 plus lambda. So, you can just check this just following the same method. In this case, you will have to find out what is the probability that x2 is less than x1. Again, you can follow the same process and you will end up with this answer. So, given n independent exponential random variables, the probability that the ith random variable will be the minimum among the n random variables is equal to the parameter of the ith random variable divided by the sum of all the parameters, right. So, we have seen today 4 properties. First, the memoryless property. Second is if you have n independent identically distributed exponential random variables with parameter lambda, then their sum has gamma n lambda distribution, and I have explained what gamma n lambda distribution is. So, it is a continuous random variable having a certain probability density function. So, that was the second property. The third property was that if you take n independent exponential random variables, each having their own parameter lambda I, then the minimum of them has again exponential distribution with parameter the sum of the parameters. And the last property that we saw is that again if you are given n independent exponential random variables having like possibly different parameters, then the probability that the ith random variable will be the minimum among the n random variables, that is given by the parameter of the ith random variable divided by the sum of the parameters, right. So, you will see that all these properties we will be needing when we look at Poisson processes. When we try to prove various properties of Poisson processes, we will need these properties. So, this lecture, and we will be having one more lecture at least on exponential distribution. So, these are all preparations for Poisson processes. Fine. Okay. So, we will stop here today. Thank you all.